So the team is composed of 4 people. Leo is from PSC, and he's been developing this project for a month before the Hacker House started. And the 3 of us, Yo-Yo, Even, and me, Steve, we are joining the team. And since then, we've been like working on writing the backend logic, the libraries, and also additional front end for the project. So just giving a brief introduction about Leo, probably not my thing to do, but he has 20 years of experience in software engineering and has been a co-founder and CTO and started his blockchain journey in Gitcoin and now has been working on ZKP EVM of Ethereum Foundation. And that's why this project was born, because he noticed that there's been lots of standardized code and also potential ways to simplify or standardize the circuits within ZK EVM. For the rest of the team, Yo-Yo is the founder of Titration Labs, and he's also been a researcher for both AI and ZK. And Even is the developer and auditor at SegBit, which is a blockchain security company, but also has a sizable focus on zero-knowledge proof, especially its education. Myself, I'm Steve. I am a dual degree student from University of Pennsylvania at Wharton, doing a degree in computer science and also business administration. So the Chiquito project concerns with only a small part of the whole like bigger zero knowledge proof kind of ecosystem. And the whole system is composed of like academics writing papers about proof systems, and then programmers or like designer of languages will implement these into like circuits. However, there's been a large barrier in terms of going from the proof system to the circuit, and even going from like the circuit language to actually designing the circuit. And we believe that to solve this problem, we definitely need some like higher level tools to make it simpler for the mass, or not really the mass, but just a general programmer to onboard onto like circuit writing for the ecosystem. So again, the problem statement is that writing Hill2 circuit is very cumbersome. For example, for the ZKEVM, with lots of complexity, abstraction is inevitable. So with like greater abstraction, we can not only simplify the circuit writing, but also enable like additional complexity for writing more complex circuits. And that's why we need like better and higher level tools to implement this vision. And that's why we have Chiquito, which is a high-level language abstraction that makes the Plonkish machine compilation more simple. And currently, we've implemented a couple features. So first is that we have a working prototype that passes the test of one of the bytecode circuit of ZKEVM. And we also have a domain-specific language in Rust that the user can interact with. So if you know Rust, you know how to write Chiquito with some additional grammar. And then we also have a backend in Halo2. But again, these are very composable and very modular, as I'll be mentioning later. And all the Chiquito circuits can compose with other like pure native Halo2 circuits as well, which means you don't need to migrate the entire thing to like Chiquito, but you can just write part of it, simplify the part you want to actually simplify, and then combine that with the rest of Halo2 in their like native grammar. So that's very convenient. And earlier we mentioned that abstraction enables complexity, and this graph or chart, not chart, but pictures really show you that from pure Halo2 to like some additional abstraction on Chiquito, you can reduce the size of the code because we've been running some like syntactical sugar to enable this kind of things to happen. And this also means that you can write more complex circuits given the size is like significantly reduced. On the architecture of the project, so this is a very typical compiler for any intro to compiler class you're going to take. It starts from the domain-specific language, which compiles into a abstract syntactic tree. And then with the compiler, it's going to compile into an intermediate representation, which is going to finally translate into a regular Halo2 circuit using a Halo2 backend we've written. And on the bottom half of the graph, you see that we can actually have multiple front-end or back-end given the modularity nature of this project. So you can not only have DSL in Rust, but you can also have it in Python, which we actually have a first pass of during the Hacker House. And then the same goes for the backend, because from the intermediate representation, it can really just translate to any additional proof system, not just Halo 2, but Sangria, for example, as well. And just as a reiteration or a summary for the advantages of the project, so abstraction is obviously the number one we've been making lots of emphasis on, and composability basically means, again, the part of the circuit can be like Chiquito, or the entirety of the circuit can be converted. And regardless of how much of the circuit you converted, it can always like be compatible with the rest of the circuit, which are written in like native Halo 2. And then modularity is another feature we just mentioned, that you can have like multiple front end and back end for the same intermediate representation and abstract syntactic tree. And it's also very easy to learn given all of these features, because we just make it very easy for the users on the user experience perspective as well. And on the architecture part of it, this is basically how a regular Chiquito circuit is composed of. So instead of having the different columns as in Halo 2, we are more of a signal-based design, which is more similar to like Circum. And you can also notice that Circum has like simpler grammar, and the same happens for Chiquito as well, given its design. And the backend is going to handle all of the like column placement for you, so you don't need to do the like column assignment and also like cell assignment per se. And besides the signals, we are also based on steps. Steps are basically different types of role. Within each step, you have like the witnesses, and then you define the constraint logics for the different witnesses. And then that's called a step type. So for the circuit, you can have multiple step types, basically as many as you can. And after that, when you actually generate the circuit, you can instantiate the circuit type and then place them in the order you prefer. And each step can be composed of like multiple Plonkish table rows, which is kind of different from like Halo 2. And then finally, we have a global trace argument. This is basically what I mentioned, that you generate the final circuit using the instances of all of these step types. And I'll just back to the signals. The forward signal and internal signals are different in the sense that internal signals only happen within the step type, and the constraints all happen within the same step instance. But for forward signals, it can happen between like different instances of step types. And this is just a graphic description for the concepts I mentioned. You can see here that the first two rows of the matrix refer to the first step type, and then the like 3 through like 5, fifth row are the second step type, and each of them is like an instantiation that's composed of multiple Plonkish table rows. And then you can see the columns are like selector column 1, selector column 2, regular column 1, and regular column 2, and within there you can see the different witnesses for like ABCD and also RTB. And from a developer point of view, they don't actually see the super role because that's all taken care of by the backend logic. They do see the different like step instances. So as I mentioned, you define different step types. And in this case, it's like step type number 1 and step type number 2. And in the trace argument, you instantiate the different step types. And in this case, we have like 3 instances of step 2 and like 2 instances of step 1. And within each step type, the witnesses and also the constraints are the same. And now I'm gonna introduce a bit into the progress at the Hacker House we've made. So we've extended the library by writing 3 additional ZK-friendly hash functions and also 1 Fibonacci circuit example. And ZK-friendly hash functions are basically ones that only involves like multiplication and addition. And we also implement additional features such as a more user-friendly syntax for the lookup tables, including auto-generating the annotation. And we also updated the documentation and have a running API documentation and README on the GitHub repo right now. And additionally, also have the Python front end for additional composer modularity. For the libraries, here are the links. I'm not going to show them, but we basically did the libraries for MIMC7, MIMC7 Sponge, and also Poseidon. These are all the ZK-friendly like hashing functions that the ZKEVM is also like using. That they only include like multiplication and also addition. We adapted most of the circuit logic from implementations in the circuit library, and have also like did some testing on these. In terms of the additional features, we enable additional user-friendly syntax for lookup tables, which includes the auto-generated annotations, as you can see from the graph for the annotation. And then we also have a lookup selector column, which enables or disables the lookup matching. And that's like a separate selector column from the global selector column of the entire circuit. And we also implemented the lookup table new features in the existing examples we have. We also made like some documentation for some high-level description, including a few like easy to start example for the new users of Chiquito for easier adoption, and also created a whole cargo API documentation that's running currently live on our GitHub repo. And the final project we did was the PyChiquito, which is a Python front end for Chiquito. And Python is very like composable, and it's great with the grammar because it's not as type safe as a Rust circuit, for example, but enables lots of like syntactic sugar that Yo is very like talented at, and he's been working on that. We also have an example demo, though I'm not able to show it here because he has the demo. But that basically adapts one of our Fibonacci circuits to the Python front end. And we also believe that given Python users are like 1 point something million across the globe versus just a couple hundred thousand. Oh, sorry, probably wrong with the magnitude, but like 15 million-ish for Python and like 600,000 for Rust. So there's like a magnitude of like 20 times the difference between them. So making a Python front end will definitely accelerate the adoption for Chiquito and also for like Halo 2 in general. And that's also thanks to the modularity nature of our project. Yeah, and you can see the GitHub repo link for the Python front end, and that's the reason why we call it like the highway to the infinite garden of lower barrier for adoption, because Python provides more access to greater user base. Okay, so going forward, there are a couple of things we're gonna be working on. So one is adding additional libraries, including additional gadgets, for example, the range checking, the less than arguments, which are used extensively in like ZKVM. We're also gonna work on some core Halo 2 features. For example, getting like additional syntactic sugar for constraint builders, compilers, and also backend. Additionally, we also try to pitch this project to the ZKVM team, and hopefully can integrate additional circuit, not just the bytecode example we have so far, and hopefully also conduct some performance benchmarking for playing Halo 2 versus like Chiquito. And fourth, we're gonna conduct some products research on additional CKT cell products, for example, Noir from Aztec team and also Socrates. Yeah. And finally, we're gonna extend the modularity of Chiquito by integrating and perfecting the existing and additional front ends. So go beyond just Python, and which also needs a JSON format, a standardization for the syntactic tree. And for the backend, it's more like a long shot because it takes a long time to implement, but we can implement like additional proof systems more on the long run. Yeah. Okay, so finally, definitely follow us on Discord on the PSE channel. We have a Chiquito channel within the PSE like Discord server, and we also welcome lots of community collaborations. So definitely contact us if you're interested in the project. You have a link there, and we definitely love to hear more of your ideas on how to make our project better. So that should be it. I don't have a thank you slide for this presentation, but yeah, thank you for sticking through. And again, this is a makeup sort of presentation for the Hacker House, and that's why I couldn't cover the awesome things that you did for the Python front end. But you get the overall idea of what we did at the Hacker House.